please open the 37. This presentation is evaluation of measuring and physical properties of different digital intraoral sensors. From Dr. Wisam Al-Rawi.
Yes.
Please.
Yes, good afternoon, everyone. It's a pleasure to be here. I was part of the digital subcommittee formed at Case Western Reserve to evaluate the implementation of digital radiography at the school. And as you may know, going with digital radiography, especially intraoral sensors, it saves you time, it gives you better image quality, and it has less radiation dose to the patient. And I evaluated different latest generation CMOS sensors, the Sirona Zayas, Gendex GX700, the Kodak 6100, also the Dexis Platinum, Planmeca Pro sensor, XDR E2V, and the EVA Plus sensor, plus the Schick Elite. So I covered almost all the major sensors on the market. If you look at the component of a digital intraoral sensor, you have first the plastic casing. You have also a scintillator layer that converts the X-ray photons to a light photons. And then you have a fiber optics that leads the photons to a CMOS layer, which basically takes the light photons and convert them to electrical signal that is later on passed down to an electronic layer and then transmitted to the computer. Some of the sensors, they have a protective shielding to absorb the radiation that passes through the CMOS layer, which is basically useless, but it adds radiation burden to the patient. In order to compare all the images and in order to establish a benchmark for comparing different intraoral sensors, I had to align all the sensors so that the X-ray beam comes perpendicular to the sensor surface. And we used the rectangular collimator. We placed it on a plastic cup, and then we used the heavy body to basically connect the sensor to the rectangular collimator. And as you can see on the left image, you have the Planmeca X-ray machine. It's the Intra machine. It's a digital X-ray machine, and you can see the exposure settings that we used. In order to compare the optical resolution, we used a line pairs tool. This is from Gamex, and as the line pairs go up higher, it becomes harder for a system to resolve 2 points close together as 2 separate points rather than a single point. So the higher the line pairs number, the higher the resolution or the optical resolution for that specific sensor. So we compared the sensors using the same tool. The highest one was the Kodak sensor. We were able to see and distinguish all the lines from top to bottom at 20 line pairs per millimeter. I zoomed in a lot here, so it looks better probably on a computer monitor compared with a projector screen. This is the Schick sensor, and as you can see, probably you can get maybe between 13 to 14 line pairs. I have also an image from Planmeca, and as you can see, 14 looks okay, 15 looks okay in some parts, but you lose some of the details in other parts. So we always use the lowest number where you can see the entire lines from top to bottom. The EVA sensor from ImageWorks performed the worst among the other sensors, and it's really have a very hard time getting line pairs maybe above 8 or 9. And unfortunately, the line pairs are very important when doing an endodontic treatment, and our endo residents used to use this sensor. They were wondering why the image quality looks bad. We also had designed a contrast phantom, basically made of a block of aluminum with a stair step. The accuracy for this line pair was 0.01 millimeter. We used a CAD/CAM machine to manufacture this, and it has a different hulls with different depths. And basically, you should be able to see the different hulls when you take a radiograph. It also has an acrylic resin that you place on top of the metal component to simulate soft tissue scattering. Here are some of the images that we got. As you can see, this is the Schick Elite, and you can see the dots 1, 2, 3, 4, 5, 6, 7. And as you go, you miss some of the dots. You are able to see the other dots. This is another example from the Kodak sensor. Again, you can see the 7 dots, but as you go higher, you lose some of the definition in that area. The XDR sensor was having a hard time calibrating the grayscale values. And as you can see, it's very hard really to see the holes in the shallowest area of the aluminum block, but you can still see them on the other side. In order to measure the active area of a CMOS sensor, XDR provided us with an aluminum or a copper mesh, and each small square represents a 1 millimeter square area. And basically, when you expose this mesh by placing it on top of the sensor, you can go and count the squares, and it gives you the active area, both the width and height in millimeters. So this way we can compare the active area for different sensors. This is the Zias Plus sensor. This is the Dexis Platinum. Dexis basically cuts the corners also from the other side. So the manufacturer has the liberty to design the sensor the way they want the sensor to be. For Dexis, they did this design. They told us basically to kind of make it more comfortable to the patient, but maybe more study needed to be done in order to evaluate that. We also wanted to know if a sensor has a backscatter shield to absorb unnecessary radiation, and we also wanted to know the number of wires. The number of wires, basically the higher the number of wires inside the sensor, if any of those wires got damaged, basically the sensor cannot be used. So what we did is that we took a sensor and we placed it on top of another sensor, and then we exposed the sensor. So we were able to see inside the sensor. In this example, you can see the Gendex sensor. This is at 80 kVp, and you can see that you have a good backscatter shield, maybe a little bit less in this area. It comes with 4 wires inside. This is the Kodak sensor. Kodak sensor at 70 kVp, we did not get any image. Basically, the shield blocked all the photons. At 80 kVp, we were barely able to see what's going on inside the sensor. We had to go to the highest exposure level just to be able to take a peek inside the sensor. And you can see that you have 6 wires on this side, 6 wires on the other side. So Kodak has basically 12 wires running inside the cable. And the cable is a little bit thicker compared with other sensors. This is the Planmeca sensor. Again, a backscatter shield except in this area. You have 2 wires running inside. The EVA Plus sensor did not have any backscatter shield at all. And you can see you have a very dark image of 80 kVp. When we lowered the kVp to 70 and we took a look or a picture of the cable, you can see that you have so many wires running inside the cable. That's the XDR sensor. Again, the XDR sensor does not have a backscatter shield, but it has 4 wires inside. So what we did is that we formed a table, a summary of our findings, and on top, on the columns you see the sensors, and on the rows you see different specifications. And as you can see, that the highest resolution was probably for the Kodak sensor. Dexis sensor was of a particular interest because although they say the sensor is 2.2 megapixels, by default they set it to 0.5. And unless you go and change that, you basically take images at a much lower resolution. If you look at the advertised bit depth, which is basically represents the grayscale values, most sensors have 12 advertised. Dexis advertised to have the highest bit depth, 14, which is basically 16,000 shades of gray. But what we found is that during the testing that their software only supports 8. And this was confirmed by their engineers. Schick sensor of a particular interest, basically they did not provide any technical specification. And we contacted the company, we told them we want to know about the technical specification of your sensor. They said no, nobody should know about that. It's information forbidden from the general public. And basically we used the phantoms to be able to get all the information that we needed. So in terms of advertised line pairs, here you see the values of different vendors that they advertise. And then the tested line pairs, you see that XDR was very close, Kodak was very close, DEXIS was a little bit less. By default, you get the 12 with a lower resolution. With the highest resolution, you get 17. Schick, you get 13. Planmeca, 13. Denix, you get 8. Some sensors, they come either as direct USB or they have an interface box to connect to the sensor. So we listed that here. Planmeca and Sirona, they have an Ethernet option. So you can plug the sensor directly to the network rather than to the computer itself. We also measure the plate thickness using a digital caliper. And the thinner the sensor, it's more easier to place it inside the patient mouth. And as you can see, DEXIS was the thickest sensor among the group. The advertised active area, this is what they say. And below, we got the value very close to what the manufacturer was giving us. The surface area represents the total surface area of the sensor, or the plastic of the sensor. And if you took the active area and divide by the surface area, you get the total utilization of the surface of the sensor. And basically, you want more active area and less plastic. And most of the sensors, they scored around 70 to 65. DEXIS was probably the highest with 74. And this was measured for a size 2 sensor. Once you go to size 1, the value becomes less. And when you go to size 0, you are basically around 55% utilization. Thank you so much for your time.
Okay, thank you very much. Nice presentation. And please, have a question? Comment?
Yeah. Thank you for the excellent presentation. My name is Louis Seller from Germany. Question: do you plan to extend it to solid phosphor plate scans?
Well, we will be looking at the phosphor plates as well. We took an image for the regular film as well in order just to compare it with the findings. But we really didn't look at the phosphor plates. I think it would be nice to have that included. And we kept all the images in TIFF uncompressed format, and we plan to put them online, free for everybody, so you can just go and download them and compare them for yourself.
Thank you very much.
Thank you.
Thank you. Very nice presentation. I'm interested in dosimetry. Did you measure relative sensitivity, or I'm not sure I accept your initial generalization that there's a dose sparing effect from going digital. And it would be interesting to look at the comparative comparative sensitivity of each of the different sensors.
Yeah. Well, when we initially started testing the Planmeca sensor and the Schick sensor, we had the company telling us the exposure time. And we were using 0.2 second for anterior teeth. When we switched to digital, the same X-ray machine has a digital settings, and we went from 0.2 to 0.05, which is basically about 75% reduction in exposure time. When we went to 0.2, the sensor was saturated so much we did not get any image at all. And for almost all the sensors, we were around 0.05, 0.64, 0.064.
So this is compared to F-speed film?
F-speed film, yes.
That's pretty remarkable. I'm very interested in that. But how about the comparative sensitivity of the different sensors that you
We included that we had the signal to noise ratio phantom, and we took exposure time from 0.01 to 0.2 seconds. And we plan to basically do a signal to noise ratio analysis, and hopefully we will be able to get a plot or a graph showing us different sensitivity of the sensors. Yes. Thank you.
Okay, thank you very much. We got a nice presentations and very good discussion.